Infrared radiation was discovered by Sir William Herschel in 1800, where he related this radiation to heat. Today we realize that once we heat up matter, the atoms or ions start to vibrate faster, which is then related to heat absorption. With this idea in hand, it was believed that infrared light with specific wavelengths could provide information on this matter, and it turns out that this part of the electromagnetic spectrum is able to measure the vibrations of atoms in matter. These vibrations then can be measured by radiation of similar energy and thus wavelengths, which occurs in the infrared region of the electromagnetic spectrum. The bigger the molecule, the more possible vibrations there are. In a diatomic molecule, such as for instance carbon monoxide, only one vibration is possible, whereas in a nonlinear free atomic molecule, such as water, already three vibrations can be distinguished. In crystalline solids, the number of vibrations is limited because most of the vibrations of the various atoms or ions are the same due to the symmetric nature of the crystal. But what can infrared analysis contribute to battery technology? The synthesis of many battery materials use solvents and additives of organic nature, which all have clear infrared absorption peaks. Therefore, measuring these at different stages during the synthesis would provide information of the status of the reaction. Infrared analysis can also be used to verify the quality of the synthesized material. With optical fibers mounted in a battery, it is possible to monitor the formation of unwanted species and so to verify the state of health of the battery. In the same aspect, post-mortem analysis can give answers on which parasitic reactions took place during the lifespan of the battery. It is nevertheless stressed that infrared light, being electromagnetic radiation, can only be absorbed if vibration results in polarization, an important prerequisite of absorption in electromagnetic radiation in general. That means that the atoms or ions in molecules or crystals should be essentially different. Therefore, once the atoms are all the same, as for instance in hydrogen gas and crystalline silicon, there is no absorption possible. To measure, however, these vibrations, the atoms need to be polarized, which is done with a strong laser. This method is referred to as Raman spectroscopy. Infrared and Raman spectroscopy are thus quite complementary, which can be seen in a recorded spectrum with silicon as an example. The absorption spectra for infrared and Raman spectroscopy are not plotted as a function of frequency or energy, but using a strange dimension of the inverse centimeters or reciprocal centimeters. This is called the wave number, but it will anyhow reflect a frequency or energy. In the case of silicon, we can clearly see a strong absorption peak using Raman spectroscopy at 500 inverse centimeters, which is absent in the infrared spectrum. The small peak at 1200 inverse centimeters is due to the oxidation of the silicon surface, which is a silicon dioxide, and this can be seen in the infrared spectrum. This clearly shows the complementary of both measurements. It is also interesting to identify delicate differences in atomic or ionic arrangements in a crystalline structure, something that might be relevant for identifying the actual structure of any electrode material. One of the interesting electrode materials with a very high potential of 4 to 5 volt in a lithium-ion battery is lithium nickel manganese oxide, lithium 1, nickel 0.5, manganese 1.5 and oxygen 4. Here the nickel and manganese are distributed in the cubic crystal either very ordered or randomly. Ordered structures would give us more vibration peaks than disordered structures, which can be nicely measured with Raman spectroscopy. Both structures have the same arrangements of the oxygen ions in the cubic structure, but have different arrangements of the nickel and manganese. Similar results would be achieved, however, with infrared spectroscopy, but in this case, Raman spectroscopy would give us a little more detail.